All right, welcome to the Bio 110 Bioenergetics Lecture 2. I'm going to try to record this again after I lost all the work that I did originally. In this lecture, we're going to learn about glycolysis, and after glycolysis, we're going to learn about the process of fermentation. So glycolysis is one of the central ATP and electron carrying pathway that the cell has. It is a process that can happen in the absence of oxygen. So glycolysis can happen in cells which are growing anaerobically and cells that are growing aerobically. The process of glycolysis involves a molecule of glucose that is going to undergo a series of catalytic steps and eventually will be converted from a 6-carbon glucose molecule into 2 3-carbon pyruvic acid molecules. In the process, you are going to have two different phases. The first phase, it is the energy investment phase, where the cell will put in and chip 2 ATPs to charge the glucose molecule to help them make it easy to break the bonds between the carbons. The second step is going to be the energy harvesting phase, where the cell will be able to take each of the intermediate phosphorylated 3-carbon glyceraldehyde 3-phosphate molecules and be able then to harvest energy in the form of NADH, or reducing power, as well as 2 molecules of ATP per molecule of glyceraldehyde 3-phosphate that goes to the process. So the process is happening in 2 different branches by 2 different glyceraldehyde 3-phosphate molecules. You have a gross amount of 4 ATP molecules and 2 NADH molecules being gained. But since the cell invested 2 ATP, the net gain of ATP is going to be 2 ATPs per glycolysis molecule. Glycolysis is going to start with 1 molecule of glucose, a 6-carbon sugar molecule. Through a set of 10 steps, that 6-carbon glucose molecule will be broken into 2 molecules of pyruvate. Through this, as we mentioned earlier, you're going to have an energy investment step, and that energy investment phase is going to happen on step 1 and step 3 of the process. An intermediate that you're going to obtain after the second phosphorylation, it's going to be fructose 1,6-bisphosphate. And through 2 different reactions, that fructose 1,6-bisphosphate will be cleaved into 2 glyceraldehyde 3-phosphate molecules. Each of those 2 glyceraldehyde 3-phosphate molecules will go through identical steps, step 6, 7, 8, 9, and 10. And through that, it's going to be the energy generation phase, where you obtain 2 NADHs and 4 ATP. As I mentioned earlier, since you already invested 2 ATP initially, you're going to only get a net gain of 2 ATP. Now, let's take a look closer at the initial energy investment steps. The first energy investment steps happens when glucose comes inside the cell in the cytoplasm. So, I forgot to mention, all the steps of glycolysis are going to be happening in the cytoplasm. So once glucose gets transported across the cell membrane, it's going to immediately be phosphorylated by the enzyme hexokinase into glucose 6-phosphate, meaning that a phosphate will be added to carbon 6 of the glucose molecule. One thing that is going to happen to that glucose molecule is that it will be isomerized to a fructose 6-phosphate molecule. And later, on step 3, that fructose 6-phosphate molecule will be phosphorylated by the enzyme phosphofructokinase to obtain a fructose 1,6-bisphosphate. As we mentioned a moment ago, fructose 1,6-bisphosphate will be the molecule that will be cleaved to eventually generate 2 glyceraldehyde 3-phosphates. So again, in step 1 and on step 3, They are the initial step where you have an investment of energy by the cell by spending 2 ATPs to generate a phosphorylated intermediate fructose 1,6-bisphosphate. After the fructose 1,6-bisphosphate had been eventually broken down into 2 glyceraldehyde triphosphate molecules, we begin with the steps that are going to be generating energy. So on step 6, the glyceraldehyde triphosphate molecule will be used by the enzyme glyceraldehyde triphosphate dehydrogenase to generate an intermediate that is going to be 1,3-biphosphoglycerate. In the part of the process, you're going to recruit 2 inorganic phosphate molecules that are going together with the NAD plus generate 2 NADH as well as 2 protons. At the end, as you can see, the glyceraldehyde triphosphate, which originally had a phosphate at position 3, now is going to be converted into 1,3-bisphosphoglycerate that has also another phosphate molecule at position 1. The next step of glycolysis will now involve the initial generation of ATP through substrate level phosphorylation. So here, that molecule, 1,3-biphosphoglycerate, of which we have 2, will be dephosphorylated by the phosphoglycerate kinase molecule to generate an ATP molecule. So from 2 biphosphoglycerate molecules, you're going to obtain 2 3-phosphoglycerate molecules as well as 2 molecules of ATP. In a moment, we're going to take a closer look at the reactions of how this is happening. But as I mentioned earlier in the class, what we have is that ATP synthesis is happening in glycolysis by substrate level phosphorylation, where the substrate that is phosphorylated will be able to donate that high energy phosphate to ADP to generate an ATP molecule. So let's take a look at how the process of the energy harvesting and preparation happen in reaction step 6 and reaction step 7. So on reaction step 6, we have the glyceraldehyde triphosphate and NAD+, which are going to be bound by the enzyme glyceraldehyde triphosphate dehydrogenase. As part of that process, what you're going to have is the oxidation of glyceraldehyde triphosphate to release a reduced molecule of NADH from NAD+. The intermediate that you can see here in the image, it's the formation of a covalent bond between the glyceraldehyde triphosphate with the enzyme. The enzyme possesses a thiol group, an SH group. And through that, the enzyme is going to be able to form a covalent bond between it and the glyceraldehyde triphosphate. Now, when glyceraldehyde triphosphate is oxidized, you're going to have the conversion of this hydroxyl group in carbon 1 to a carbonyl group in carbon 1. And that bond between the enzyme and the carbonyl group becomes a thioester bond, which is a very high energy bond. So that very high energy bond is going to be formed between the glyceraldehyde triphosphate and the enzyme glyceraldehyde triphosphate dehydrogenase. At that point, also by this enzyme, you're going to have an incoming inorganic phosphate, and that incoming inorganic phosphate will be able to displace the high energy thioester group to form a high energy phosphate bond, generating at the end and adding a phosphate at position 1, and therefore generating a 1,3-bisphosphoglycerate. Now on step 4, 1,3-bisphosphoglycerate it's going to be used by the enzyme phosphoglycerate kinase to generate an ATP by breaking out the bond between the phosphate and carbon 1 of 1,3-bisphosphoglycerate, and therefore that high energy bond can be used to generate the energy and form a new ATP molecule. At the end, you'll end up with a 3-phosphoglycerate molecule that still has a phosphate at position 3. So this is another illustration of ATP being generated by substrate level phosphorylation. Now, when we look at the cell, we can observe that the cell possesses multiple phosphorylated intermediates. These phosphorylated intermediates have very different delta G's for hydrolysis of their bonds. Here in the red box, I have marked ATP. And when ATP is hydrolyzed to ADP, it has a delta G for hydrolysis of minus 7.3 kilocalories per mole. But what you can observe is that other phosphorylated intermediates have a lot more energy. The first one here at the top, phosphoenol pyruvate, has a delta G for hydrolysis of minus 14.8. Another one, 1,3-bisphosphoglycerate, which is also part of glycolysis, as well as phosphoenol pyruvate, has a very high energy delta G for energy for hydrolysis, that is 11.7 kilocalories per mole. Creatine phosphate, which is the molecule, the high energy phosphorylated intermediate that we have in muscle cells, also have a higher delta G for hydrolysis than ATP at minus 10.3. This is the molecule that is able to replenish the ATP stores in muscle cells when they are depleting by donating its phosphate to ADP to generate ATP for the muscle cell to use. Other molecules like glucose 6-phosphate has a lot lower delta G for hydrolysis. So two things I want to point out about this type of molecules. What you can see, the first thing that I want to show you is that these phosphorylated intermediates are very transient, and they are not designed to store energy for the long term of the cell. The cell will store energy for long term in the form of fat or in the form of polymers of glucose like starch or glycogen. The other thing that I want to show you is that the ATP and ADP pair, it's a molecule that has an intermediate delta G for hydrolysis. That means that the molecule of ADP would be able to accept energy and phosphates from phosphoenol pyruvate or 1,3-bisphosphoglycerate to generate ATP from substrate level phosphorylation. The same way, ADP will be able to accept a phosphate from creatine phosphate to generate ATP. On the other hand, ATP, being here an intermediate molecule, it's able to donate its phosphate to a molecule like glucose to generate a glucose 6-phosphate, and therefore generate a high energy intermediate that will later be used in the cell. So by having this intermediate delta G for hydrolysis energy, ADP is able to accept phosphate and energy from other phosphorylated intermediate with much greater energy, delta G energy for hydrolysis, and ATP will be able to donate a phosphate to other molecules with much lower delta G for hydrolysis energy. Now, let's look at how the cells uses glycolysis as a way to form ATP in an energetic favorable way. So what we're going to look here are at the step 6 and step 7 of glycolysis. And what we're going to look is at the change in free energy here on the left. One of the initial reactions is going to be the reduction of NAD plus into NADH with the concomitant oxidation of glyceraldehyde triphosphate into phosphoglyceride triphosphate, which is going to have the decrease in free energy. However, you are also going to have the formation of the high energy bond. So the phosphoglyceride triphosphate will be receiving a phosphate at position 1 and therefore become 1,3-biphosphoglyceride. At the end, you have a molecule with a very high free energy. In the second set of reactions, step 7, you have now the donation of 1 phosphate from 1,3-biphosphoglyceride, and you're going to have a great release in free energy by the hydrolysis of the high energy bond between the phosphate and the in position 1 in bis-phosphoglyceride, as well as the reaction that has a free high energy of ADP gaining a phosphate to generate ATP. So at the end, because the free energy of the hydrolysis of that high energy one it's greater than the free energy of ADP getting a phosphate to become ATP, this is able then to push the reaction to generate ATP. At the end, you end up with a molecule of 3-phosphoglyceride. Now, in the next step of glycolysis, we have the last production of ATP. And here we have a molecule of phosphoenol pyruvate, which has about a 14.8 kilocalories per mole of delta G energy for hydrolysis. That molecule, it's going to be catalyzed, that reaction is going to be catalyzed by the enzyme pyruvate kinase that is going to be able to remove that phosphate from phosphoenol pyruvate and generate a molecule of pyruvate and ATP. Since we have 2 molecules of phosphoenol pyruvate, we'll be ending up with 2 molecules of pyruvate and 2 ATP molecules. Therefore, during glycolysis, the net gain of ATP will be 2 molecules. Again, just to remind you, a kinase is, in general terms, an enzyme that can add a phosphate to a substrate. So in this case, it was discovered because you can take pyruvate and phosphorylate it into phosphoenol pyruvate. Now, let's look at the film from the book to understand the understand the process of glycolysis in a little more detail.
Cells break down food molecules, such as glucose, through multi-step pathways. In the process of glycolysis, the breakdown of one glucose molecule into 2 3-carbon molecules produces a net gain of energy that is captured by the molecules ATP and NADH. In eukaryotes, the breakdown product, pyruvate, is imported into mitochondria, where it ultimately feeds into the citric acid cycle and the electron transport chain. Glycolysis involves a sequence of 10 steps. In the first 3 steps, energy in the form of ATP is invested to be recouped later. In the 4th and 5th steps, this energy allows glucose to be split into 2 smaller molecules from which energy can be harnessed efficiently. And in the last 5 steps, energy is released stepwise as ATP and NADH. The elegant chemistry that evolved to catalyze these reactions ensures that energy is released in small portions that can be efficiently captured. Less controlled combustion reactions would release most of the energy as heat. In the first step, the enzyme hexokinase uses ATP to phosphorylate glucose. This investment of energy primes glucose for energy-releasing reactions later in glycolysis. The resulting molecule is glucose 6-phosphate. ADP is released. This first step of glycolysis is irreversible. In the second step of glycolysis, the enzyme phosphoglucose isomerase catalyzes the opening of the ring form of glucose 6-phosphate to the open chain form. The same enzyme then performs a reversible reaction in which the carbonyl group of glucose 6-phosphate changes position from the first carbon to the second carbon in the chain. This reaction involves a water molecule, which donates a hydrogen ion to the carbonyl oxygen. The hydrogen ion is then retrieved from the hydroxyl group on the second carbon, creating a new water molecule. In the process, fructose 6-phosphate is formed. The same enzyme, phosphoglucose isomerase, catalyzes the formation of fructose 6-phosphate into its ring form. In the third step of glycolysis, the enzyme phosphofructokinase uses ATP to phosphorylate fructose 6-phosphate. ADP is released, and the molecule fructose 1,6-bisphosphate is formed. This third step, in which the second phosphorylation event occurs, is irreversible and is a major regulatory point in the commitment to glycolysis. The phosphorylations in steps 1 and 3 represent an investment of energy that will be paid back in the later stages of the pathway. Step 4 of glycolysis begins with the opening of the ring form of fructose 1,6-bisphosphate into its open chain form. In this step, the enzyme aldolase cleaves fructose 1,6-bisphosphate into two molecules. One molecule that is formed is the 3-carbon glyceraldehyde 3-phosphate. The enzyme performs additional reactions on the second 3-carbon molecule. The second molecule is dihydroxyacetone phosphate. In step 5 of glycolysis, the enzyme triose phosphate isomerase catalyzes the isomerization of dihydroxyacetone phosphate into glyceraldehyde 3-phosphate. The catalytic mechanism of this enzyme is very similar to that of phosphoglucose isomerase back in step 2. The result is 2 molecules of glyceraldehyde 3-phosphate. All of the subsequent steps of glycolysis will occur twice, once for each molecule of glyceraldehyde 3-phosphate. These are the energy generation steps of glycolysis. In step 6, the enzyme glyceraldehyde 3-phosphate dehydrogenase uses NAD to oxidize glyceraldehyde 3-phosphate. The resulting molecule is connected to the enzyme by a high-energy thioester bond. A molecule of inorganic phosphate displaces the high-energy thioester bond, forming a high-energy acyl anhydride bond. The resulting molecule is 1,3-bisphosphoglycerate. In the 7th step, the enzyme phosphoglycerate kinase dephosphorylates 1,3-bisphosphoglycerate. The high-energy phosphate is transferred to ADP, forming ATP. The 3-carbon molecule is now 3-phosphoglycerate. Because this reaction occurs twice, once for each 3-carbon molecule, a total of 2 ATPs are generated. At this point, the energy investment from the first 3 steps has been paid back. In the 8th step, 3-phosphoglycerate, which has a relatively low free energy of hydrolysis, is transformed by the enzyme phosphoglycerate mutase into 2-phosphoglycerate. In the 9th step, the enzyme enolase removes a water molecule from 2-phosphoglycerate, creating phosphoenol pyruvate. The loss of water redistributes energy within the molecule, creating a phosphate group with an extremely high free energy of hydrolysis. In the 10th and last step of glycolysis, the enzyme pyruvate kinase transfers the high-energy phosphate group to ADP, forming ATP and pyruvate. In the second half of glycolysis, many of the reactions release energy, captured in the form of ATP and NADH. Overall, the net energy produced in glycolysis from a single molecule of glucose is 2 molecules of ATP and 2 molecules of NADH. The chemistry of glycolysis is conserved all the way from bacteria to animal cells.
Okay, let's go to the next slide. So let's just review for a second. What we have in glycolysis, it is the conversion of one glucose molecule into 2 pyruvate molecules, and those 2 pyruvate molecules can later have different fates. We're going to look into that in a moment. In addition to 2 pyruvate molecules, we're going to have the generation of 2 NADH molecules, as well as a net gain of 2 ATP. Now, the fate of the pyruvate after glycolysis is going to depend on the availability of oxygen. On the right, we have a situation where oxygen is present, and therefore pyruvate will be transported across the membrane of the mitochondria to participate into the citric acid cycle reactions as well as the electron transport chain. In the other hand, on the left, what we have is a situation where we have low or no oxygen available. And at that point, what we are going to have is either anaerobic respiration or the process of fermentation. Fermentation is going to be of 2 different kinds in eukaryotic cells. And one of them is going to be the production of lactic acid in muscle cells. We're going to look into that. Or the production of alcohol and carbon dioxide in yeast cells. Just remember that if we're looking then at glycolysis, glycolysis is a process that happens exclusively in the cytoplasm of the cell. Fermentation also will happen in the cytoplasm of the cell, whereas the process of respiration, the citric acid cycle, and electron transport chain are going to happen in the mitochondria. Now, what happens in the absence of oxygen? In the absence of oxygen, we're going to have one of 2 processes, either anaerobic respiration or fermentation. Now, in the presence of oxygen, oxygen will be the ultimate electron acceptor during respiration, generating a water molecule. But in the absence of oxygen, what you're going to have, it's an anaerobic situation, whereas you can then have anaerobic respiration. And in anaerobic respiration, you have an event that is happening in the absence of oxygen, and therefore another molecule is the final electron acceptor. One of those such molecules can be ferric iron, or iron plus 3, and that molecule is going to be reduced into ferrous iron, which is iron plus 2. Or you can have nitrate that is going to be reduced into nitrite. All this anaerobic respiration will also involve an electron transport chain, and oxidative phosphorylation, which is the generation of ATP using a proton gradient. On the other hand, what you have is the process of fermentation. And fermentation, as I mentioned, could be the lactic acid fermentation that happens in muscle cells, or it could be the ethanol and carbon dioxide fermentation that happens in yeast cells and some bacteria. That reaction happening in the cytoplasm, it's designed to recycle and therefore oxidize NADH to NAD+, and that NAD+ will be reused in glycolysis to generate more ATP. Let's take a look at these 2 pathways. These 2 pathways of fermentation are going to have in common that the initial generation of pyruvate will happen through glycolysis. And as we mentioned, the initial glycolytic pathway is going to generate 2 ATP and is going to generate 2 NADH molecules. Now, from pyruvic acid, you're going to generate lactic acid. And in the process, NADH is going to donate its electrons to pyruvate, to generate lactic acid, and that is going to give you a reduced NADH plus molecule. As the arrow here in red indicates, that NADH plus molecule, it's going to accept electrons later to generate an NADH molecule in glycolysis. In the lower area, we have again the same process of glycolysis providing 2 pyruvic acids, 2 ATPs, and 2 NADHs from one glucose molecule. What we also now have is the initial decarboxylation of pyruvic acid into acetaldehyde, and acetaldehyde, not shown here, will then be reduced to generate 2 ethanol molecules. NADH will be oxidized and donate its electrons to generate an NAD plus molecule, which again, follow the red arrow, will be able to accept electrons later in glycolysis to help generate ATP. So the process of glycolysis can be now summarized here in this graph, in this picture, excuse me. Again, glucose being undergo glycolysis, and during glycolysis is going to generate 2 pyruvate molecules. The system will provide then 2 ATP net and 2 NADH molecules. Now, the pyruvate molecule is going to accept an electron from NADH and be reduced to form lactate. Look at the carbonyl group here in pyruvate that will become a hydroxyl group in lactate. The generated NAD plus that is the product of the reduction of pyruvate now can go and participate in glycolysis to generate more NADH, and because of that the system can continue to produce ATP through glycolysis to feed the cell. On the other hand, in a yeast cell, you're going to have the same process of glycolysis, generating 2 pyruvate molecules from one glucose, 2 ATP molecules, and 2 NADH molecules. So the first step in fermentation in yeast will be to take and decarboxylate the pyruvate molecule into an acetaldehyde molecule. That acetaldehyde molecule will be able to be reduced by gaining the electrons from NADH into ethanol. And you will have then an NAD plus molecule resulting from the donation of the NADH electron to acetaldehyde. That NAD plus molecule can now recycle itself and go back to participate in glycolysis, driving the production of ATP as well as NADH. With that, I'm going to finish this lecture, and next time we'll talk more carefully about the citric acid cycle, as well as begin to understand the initial steps of the electron transport chain.